We will discuss one of the numerical based on equilibrium of forces. So the question is a train is moving along a horizontal track and the pendulum suspended from the roof of the train makes an angle of 4 degree from the vertical with the vertical. So find the acceleration of the train. So let A be the acceleration of the train. Let A be the acceleration of the train. And the pendulum is suspended from the roof. This is the roof, and the pendulum is suspended from the roof makes an angle of 45 degree with the vertical. This is the vertical line, and pendulum is making an angle of 4 degree with the vertical. Pendulum is making an angle of 4 degree with the vertical. And this is pendulum, its weight is acting downward, which is mg, and tension force acts in upward direction. Force of tension acting in upward direction. And this is the weight of pendulum which is acting in vertical direction. So if this angle is 4 degree, then this angle will also be 4 degree by alternate angle. So there must be two components of T. The vertical component is T cos 4 degree and the horizontal component is T sin 4 degree. These are the two components. Now we equate these forces. So T cos 4 degree is equals to mg, because mg acts in downward direction and T cos 4 degree acts in a opposite vertically upward direction. So we equate these two forces, mg equals to T cos 4 degree, and this is the horizontal force T sin 4 degree, which must be equals to the force M into A, the resultant force M into A. So T cos 4 degree, T cos 4 degree is equals to mg, the vertical force acts on the pendulum and the horizontal force acts on the pendulum is equals to M into A, mass and acceleration. Because the pendulum is affected by the acceleration of the train is in moving condition in horizontal direction. Now divide second by first. Divide equation number 2 by 1. So we get T sin 4 degree upon T cos 4 degree equals to MA upon MG. M cancelled, T and T cancelled, and Sin 4 upon cos 4 tan 4 degree equals to A into G, and we get the value of A, G into tan 4 degree. Value of G is given, and the value of tan 4 degree is 0.07. So 10 into 0.07, which is equals to 0.7 meter per second square. So this is the acceleration of the train. The acceleration of the train by which it is moving 0.7 meter per second square. Now we discuss the next question. The next topic, and that is motion of connected bodies. Motion of connected bodies. Motion of connected bodies. So take the case, there are two masses M and M are connected at the ends of an inextensible string, and the string passes over a smooth frictionless pulley. There is a smooth frictionless pulley, and two masses are connected by a string. There are two masses, capital M and a small m, and these two masses are connected by a string, and they passes over a pulley. M, capital M, is greater than a small m. So this mass will move in downward direction. This capital mass goes in downward direction. So acceleration acting on it, A, in downward direction, and this mass will go in upward direction because mass small m is less than the capital M. So acceleration, this will move in upward direction, and this mass will move in downward direction. In this mass, acceleration acts in downward direction, and here acceleration acts in upward direction. Tension acts in both the string in upward direction, T, and its weight is M into G, and this is a small m into G. So this mass is going in downward direction. It means mg is taken positive. The direction in which it is moving would be taken positive. Mg will be positive, T will be negative because it is opposite to the Mg, and these two result equals to the difference of these two forces is equals to the resultant force, which is equals to M into A. So for first pulley, for first mass, mg minus P is equals to capital M into A. This is the first equation. Now for the second mass, a small mass M. This mass is going in upward direction. So the direction of motion is taken as positive. So T is positive, then mg will be negative. And the difference between two also equals to resultant force, mass into acceleration, a small m into a small a. So T would be taken positive, P minus mg is taken negative, and this is equals to the resultant force m into a. We are interested to calculate the acceleration, the value of the acceleration A and the tension in the string. We calculate two things. One is tension and another is acceleration, the value of the acceleration A. So adding first and second. Add equation number first and second. So mg minus capital T and plus capital T minus mg is equals to m into a, capital M into a plus small m into a. Now T and T gets cancelled, and from these two terms G is taken common. So m minus m into G, and from here A is taken common. So m plus small m into A. And we find the value of A. A is equals to m minus m upon capital M plus small m into G. So this is the expression for acceleration acting in the string. So it is clear that A is less than G. The value of acceleration acting is less than the acceleration due to gravity. Now we calculate the value of T, tension, and for this we divide equation number first by second. So divide first by second. So mg minus P upon P minus mg is equals to m into a upon a small m into a. So a gets cancelled and we do cross multiply mg into m into mg minus P into m equals to capital M into T and minus mmg. So this will come on left side. So m into g, and it becomes positive m into g equals to, this will go on right side. So m into t plus a small m into t. 2 mmg plus mmg, it becomes 2 times of m into mg. And from these two terms, t is taken common. So m plus m into t. And we calculate the value of tension T equals to 2 into capital M into m upon capital M plus a small m into g. So this is the value of tension. To calculate the tension in the string, we use this formula, and for finding the acceleration produced in the string, we use this formula. Now the next topic which we discussed, free body diagram. Free body diagram. When a number of bodies are connected together by strings or rods, when a number of bodies are connected by strings or rods. When a number of bodies are connected by strings or rods, then it is convenient to consider each body. Then it is convenient to consider each body. Then it is convenient to consider each body separately. Each body separately. And to write the equation of motion for each body. And to write the equation of motion, and to write the equation of motion for each body by taking into account and all these forces acting on it. So when a number of bodies are connected by strings or rods, then it is convenient to consider each body separately. Suppose there are 2 or 3 or 4 bodies and they are connected by a string or rod. Then to calculate and to study, we separate all the bodies and then write the equation of motion for each body separately. And this is called free body diagram. This is called free body diagram. And all the forces acting on it, all the forces acting on it, then equating all the forces acting on it and then equating the net force acting on the body and equating the net force acting on the body. So separately we study the equation of motion of all the bodies, and this is called free body diagram. Few numericals we see on the few numericals we discuss based on free body diagram. The first question is, a pull of 15 Newton is applied to a rope. A pull of 15 Newton is applied to a rope. A pull of 15 Newton is applied to a rope attached to a block. Attached to a block of mass. Attached to a block of mass 7 kg. Lying on a smooth horizontal surface. Lying on a smooth horizontal surface. Lying on a smooth horizontal surface. The mass of the rope is 0.5 kg. The mass of the rope is 0.5 kg. What is the force exerted by the block? What is the force exerted by the block on the rope? We have to calculate the force exerted by the block on the rope. So, a pull of 15 Newton is applied. There is a block of mass 7 kg and a pull of 15 Newton is applied. There is a mass of 7 kg, block of mass 7 kg and a pull of 15 Newton is applied on this block. Let this pull is F1 equals to 15 Newton. A block of mass 7 kg lying on a smooth horizontal surface and a force of 15 Newton is applied on it. So let A be the acceleration produced in the block. Let A be the acceleration produced in the block. By applying a force of 15 Newton. when a force of 15 Newton is applied on a block of mass 7 kg, then suppose A be the acceleration produced on the block. So the resultant force acting is equals to sum of the masses of the block and a string, because the mass of the string is also given 0.5 mass of the rope. Force equals to mass into acceleration. Force is equals to mass into acceleration, and the force acting on the block is 15 Newton, and mass will have to take the sum of the masses of block and rope. Means the mass of the block is 7 and the mass of the rope is 0.5. So F equals to M into A. So 15 equals to 7.5 A. And we find the value of A. 15 upon 7.5, which is 2. So we get the value of acceleration. A equals to 2 meter per second square. The value of the acceleration A equals to 2 meter per second square. Now we have to find the force. So let F2 be the force. This was the block and this is the force F2. Let F2 is the force exerted by the block on the rope. Let F2 be the force exerted by the block. On the rope. Block will also exert a force, and it is F2, and the reaction force is F2 dash. From Newton's third law, the reaction force also acts, and these two forces must be equal to the mass of the block into acceleration. So F2 is equals to F2 dash equals to mass of the block 7 and acceleration we have calculated. So the force comes to be 14 Newton. So the force exerted by the block on the rope is 14 Newton. Block will exert a force of 14 Newton on the string, and the string is exerting a force of 15 Newton on the block.